This whole fucking time I was muted. Whole time. Holy shit. This whole fucking time I was muted. For how long? 17 minutes. 17 minutes I was muted. I looked at everything but my mic response. Are you fucking kidding me? Holy shit. Holy shit. I just don't even want to fucking continue at this point. I'm so fucking done. The whole almost 20 fucking minutes. Alright, well, what a waste. I recorded it. And I'm not gonna cut it out. You know, I'm not gonna cut it out, right? If I post the stream anywhere else, I'm just not gonna cut it out. I do not give a flying fuck. So, eat shit. I don't know, yeah. Okay. Alright, the force current game. The ratio of collector current to base current when the BJT is pushed into the saturation region. IC divided by IB, right? Control mechanism, the external circuit, power supply, and resistors limits IC while the user deliberately injects excess IB. Okay. It is a circuit design parameter, not a transistor property. You choose this value. Both junctions are forward biased. The base is flooded with more charge carriers than the collector power supply can pull away. The base is flooded with more charge carriers than the collector power supply can pull away. Often set to a conservative value of 10. Imagine a BGT with a manufactured BDC equals 100. The circuit load limits the maximum possible collector current to 10 milliamps. To run in active mode, you provide the transistor multiplies this by 100. To force into saturation, you need IC to hit its 10 milliamp ceiling. Mathematically, 0.1 milliamp of base current is enough. However, to guarantee saturation despite temperature shifts or component aging, you overdrive the base by providing IB equals 1 milliamp. In this saturated state, your beta forced becomes 10. Because 10 less than 100, the transistor is hard in saturation, ensuring the lowest possible voltage drop across the switch. Lowest possible voltage drop across the switch. Would you like to see how this difference affects the power dissipation and switching speed of the transistor? No. No, let's look at these real quick. $1K, 220, 800, $1K. Why wouldn't it give me a reference value? Here we have these. Oh, it's already inputting a square wave into something that is meant to convert into a square wave? That's not smart. I mean, I kind of understand. But like, I do kind of understand. So beta forced. Okay, so beta forced. All right. Okay. Okay. So we know that. We know that also. Let's see what other assumptions we can make. Okay, we know that this is going to be a 0.2 voltage drop. 0.2. That's kind of bad, but whatever. Yeah, plus, minus, right? Plus, minus. So voltage drop across here. That's that's connected through here. 0.2. This is a 9 volts. Okay. Okay. So we'll call him R1. Let's see. R1, R2, R3, R4, R5, and that's it. Okay. 0.2. Well, let's see what we can determine here. 0.2. The voltage across these. Using Kirchhoff's voltage law, we can definitely say that 9 volts. Let's not put any units for this. There's no need to do that. So 9 minus 9 minus V3, right? We're going to call this V3, positive, negative V3. We're going to call this positive, negative V5. 9 minus V3 minus 0.2 minus V5 equals 0. Okay, using Kirchhoff's voltage law. So that is true, that is accurate. We also have a couple loops inside of here. Here's a loop, right? 0.2. What would that? 0.7, 0.2. That's also a loop. We could, so what? We could solve for V2 here. Positive, negative V2. Positive, negative V1. Positive, negative V5. Okay. Looking good. 0.2. I mean, I know this. I could solve for the voltage here, right? Couldn't I? So what? Let's say, okay. So so 0.2, moving in this direction, we're going clockwise for our Kirchhoff's voltage law, or KVL, right? Let's refer to it with the acronym KVL. Okay, so 0.2 minus V2 minus 0.7, right? That's our loop right here. Equals 0. Therefore, V2 equals 0.7 minus 0.2, 0.5 volts. Okay, so V2 equals 0.5 volts. All right, that's good. That sounds good to me. So that equals 0.5. Okay, could we also use that? Not necessarily, because that's not assumed. We know that 0.5. That's the current going into, not necessarily, it's going to split between the two. Now that I know that, could we solve for that? Couldn't we, considering that that's there? Not necessarily. It would also consist of that. We know that. And we don't know him. Okay. What else? Okay, so I think we can also assume a current of 10 milliamps, right? This is what we desire, is 10 milliamps? Yeah, I believe so. Okay, maybe we can assume an collector current, IC, 10 milliamps. All right, let's go ahead and do that too. And then after I theorize this, we're going to model it in a circuit simulator, and then we're going to see how the circuit simulator's values compare and whether we get a square wave out, right? So, okay, okay, IC, again, like, same thing, so we're just not even going to change the variable name. 10 milliamps at both of the collectors. Okay, we can probably assume that this is also 10 milliamps, could we not? 10 milliamps at the collector. That's here though, so we're gonna have more going through here and then some splitting this way. But how much are we splitting this way is the question, right? Because we have this. Let's readjust that so it looks right. IC. We'll call this I1. This is it's not really IN though, but we'll call this I2. I2, I1, like that. I1, I2, IC. IC is the same here. That would supply our load, but we're not connecting anything yet, so I'm not going to really consider it. So therefore, do I know the voltage drop across him? Okay, no, because we don't know him either. We could, though, we could. Well, we're going to have a combination of the two. So there's going to be a lot of current flowing through this resistor, because there's going to be this current here and this current here. Which, could we go ahead and assume that it's going to be 10 milliamps plus 10 milliamps? That is 20 milliamps? Is that possible? Let me think. I don't think so. Here, let's hop over here and ask AI a question. Right, so 10 milliamps, 1 milliamp. So when considering emitter current, we must include base current plus, when considering, we must include base current and collector current. Yes, that's exactly correct. Your math and understanding the current relationships are flawless. Here's why your logic holds true. Blah, blah, blah. Kirchhoff's current law. Indeed. Base current. Yep. Actually, wait. Let's see something. Isn't that true, right? Because we have a 10 milliamps. Oh, it only says, wait, VCE 1 volt. Wait, VC. No, all right. Here's where I want to look. 10 milliamps, 1 milliamps, 80. Yeah, bang. So if this is, the condition under which they recorded these values, then that is also assuming a forced current gain, forced DC current gain of 10. Okay, that'll work. Right, blah, 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 existing, why this matters, active region, blah, blah, blah. Right, active region, that's where we assume that IE equals IC, but in this case, we should probably... Yeah, it's 10%. Ignoring the base current in saturation will cause significant errors, especially when calculating the exact voltage drop across emitter resistor. No. Okay, let's continue forward in our theory. Okay, I'm liking it so far, right? V2, 0.5 volts, so we determined that through KVL. Right, let me make sure, yeah, I included everything. That's going to be that right here. Yeah, we can jump that. Okay, so our emitter current, IE, should then equal 11 milliamps, right? So 11 milliamps. So, okay, that's the case. I don't know the resistance value, though we could assume it and try to solve for V3. But let's not jump to that yet. We also have 10 milliamps here, V1. Let's see, what do we know here? What do we know here? We don't know that value necessarily, though. So I wouldn't want to do that. There's nothing else I could really do there. We could go here. Is that going to give me anything? Okay, well, I could maybe make a system of equations through these two and solve for those. So, right, we have starting with R5. So V5, Yeah, minus, right? So, well, anything that's negative to positive. So if we're going to go in a clockwise direction, anything that's negative to positive is positive. So V5 plus 0.2, this is going to be positive negative, minus V2 minus, wait, that's V5. What's this? V4. Positive negative V4 minus V4 equals 0. So one equation, and what was our other one? This one, correct? But we have V3. V2. Wait, do I know V2? I do know V2. V2 is 0.5 volts. V2, so 0.5. 0.5. So now I have now I have 3 unknowns. I'm going to need a third equation. V5. V4. What's V4? Right here, this guy. Well, we can assume a current of 1 milliamp into the base. 1 milliamp, right? This is what we want to do. 1 milliamp. That's... What about to bias that? Wait, so... Okay, let's say, consider... Okay, let's come back here. Alright, I gotta figure something out. I got another question. Let's try that. No, an input voltage divider is not necessary, and your oscillator can connect directly to the base of the first transistor, as most online schematics show. A Schmidt trigger functions as a comparator. Its purpose is to monitor an external change voltage signal and snap its output high or low when specific thresholds are crossed. Would conflict with the signal coming directly from your oscillator. The operation and current requirements for the setup depend on several key factors. Right. Okay, so we'll add a current limiting resistor. That's what we'll do then. So, I think I'm going to still maintain this 10 milliamp collector current. It's fine. So let's add this current limiting resistor right here. And now I have an output of like, I can change it, right, with my potentiometer. This potentiometer right here, we can change the voltage gain. And so, I don't know, my output as of right now is like 3 volts. So, yeah, let's model it. Did this change anything? Not really. 0.7. Okay. Let's model it for, we'll see, let's just go 4 volts. Let's go 4 volts, right? Nah, yeah, I like it. Let's do 4 volts. Okay, 4 volts. Okay, where were we? I think we were solving for, yeah, we're looking at these two. Looking at this, 4 volts. You have to take this into consideration too. Is that enough? No, not really. Right, I know that this is IE, 11 milliamps, like that. Oh. Okay. Okay. Right, so we have this equation, we have this equation. We can make another equation, but we still have unknown variables. That's not really going to help us with anything. What else could I do? We have that, 1 milliamp, right? Bang. 1 milliamp. Oh, wait, I made a mistake. No, I made a mistake. So, 11 milliamps. This is going to be 22 milliamps. And that's not really IE. We'll just consider that I. What is that, 5? I5. This is 11 milliamps, and this is 11 milliamps. 11 milliamps. Yeah, 11 milliamps. Now, what is going to be our voltage here? So our voltage here, V5, what, V1, right. All of this, though, that's not really going to do anything for me. I don't know what that is. We'll accept the fact that, wait a second. VCE, which equals VBE minus VBC. So VBC. Wait, so VCE equals, okay, I guess this is also true. Can you see that? Yeah. So VCE equals VBE minus VBC. VBC. So if that's true, solving for VBC, we're going to have VBC equals VBE minus CE. So if that's the case, then we're going to have 0.7 minus 0.2 VBC. Okay, so VBC, B to C should be 0.5 volts. Okay, well then this is going to help me. So VBC equals 0.5 volts. Okay. And now this is a little different in the sense that it's positive, negative. I would believe so, 0.5 volts, right? Okay. So now we can write an equation for that. Is that still gonna get me anywhere? Shit. So no, not really. Still have a whole lot of unknowns, but we'll write it down. So what about like the node equation minus? That's not gonna get me anywhere because I don't know the value of him. I know the value of him though, but what's that gonna do for me? Maybe. Okay. Shit. Okay. So V1 minus. No, because that's just in parallel. So V1 minus V3, right? Negative, positive, positive, negative. Negative, positive, plus 0.5 plus 0.5. Negative, positive, positive, negative on this guy, right? Wait, negative, positive, negative. Wait, what the fuck? Positive, negative, positive. Okay, so plus V2, which is plus 0.5, right? V2, 0.5 equals 0. Okay, I think that is the case. So V3, V3, V5, V1, R1. I don't know, you guys seen anything? You seen any, like, any solution? Not really. 1 milliamp, R1. Ooh, 0.5 there. That's not gonna give me anything. Definitely more than 1 milliamp. How much more? How much do I have going there? Nobody cares about your updates. Fuck out of here. Yeah, I got some, some equations, but I can't quite set up a system. That's just gonna be that V1. What else do I know? Right, like I1 equals IC plus I2. That's true. I2 R2. I know IC. I don't know what I1 is. I want to solve for I1. What else do I know? I5, 22 milliamps, 1111. I know that, but I don't know what V5 is. That's not gonna give me anything. I1, 1 milliamp. I2, R3, B3. Right, 9 minus V3 minus 0.2 minus 5 equals 0. V3 minus 5, V5. So, okay. Well, using that, let's rewrite that equation. Let's come down here. 9 minus V3 minus 0.2 minus 22 milliamps. Yeah, let's keep that. Milliamps times R5 equals 0. So V3, what's a good value for R5? And then what? And then this is going to be our across V3 or across R3, our voltage across R3. And what do we want that to be? Let's look at a couple Schmidt triggers for reference. Let's see what kind of values they have. 3.9K. Let's see what else. 7.5K. 330. It's quite a difference. This one shows our thresholds. That's a really shitty sine wave. A lot of noise. Upper threshold, lower threshold. 100 ohms on that guy. Damn. Okay, I mean, there's a lot of different values. Let's assume 1,000. Let's see what we can do with that. Load a value of 1,000. Wait, so 22 e to the negative 3 times 1,000. What does that do? Okay, obviously that's not even practical. Okay, it has to be less. Yeah, much less. Wait, so 0.2, let's see. So 9 minus 0.2, right? 8.8. 8.8. So 8.8 volts equals V3 plus 22 milliamps multiplied by this resistance value R5. Okay, so if that's the case, 22 milliamps times R5, I wonder how high I want this to be. How high I want this to be. And that has to be less across here. Okay, we refer back to this equation here. Let's simplify that a little bit and consider that. So V1 minus V3 plus 1 equals 0. Okay, let's see. Wait, V3, V3, V1, V1. Almost want... Well, they can't be the same, but I do want similar values. Let me think. I'm just trying to think about like the practicality, think through it. Well, V3 definitely equals V1 plus 1. Okay. V3 equals V1 plus 1. V1 plus 1. V3 equals V1 plus 1. Okay. So therefore, let's see. 8.8. What? 8.8. 8.8. 3.8 divided by 22 e to the negative 3, 172. 172, 22 milliamps. 172. I have a 150. So what? What's okay? 22 e to the negative 3 times 150. 3.3 volts. Fuck it, let's try it. All right, 3.3 volts. So let's assume a value across, or let's assume that, what do we solve for? V3. Let's assume, V5. Let's assume V5, okay. We'll write it down here. V5 equals 3.3 volts. Let's assume this. If that's the case, then 8.8 minus 3.3, let's see how this works out, is 5.5. Therefore, V3 equals 5.5. This is all an assumption right now. If that's the case, do we have a current through V3? We do. We have 10 milliamps, or R3 rather. 10 milliamps, 5.5 divided by 10, e to the negative 3. What the heck is that? E to the negative 3. That's 550. I mean, we can achieve that. Yeah, we can achieve that. So 550, wait, that's, okay, so V5, R5 equals 150, R3 equals 550, approximately, right? Approximately, we'll figure out how to achieve that. What else? Okay, so if that's the case, then V1 is V3 minus 1. So V1 would be V3 5.5. So V1 would equal 4.5 volts. Okay, and if that's the case, we have 4.5 divided by 10 e to the negative. No, that's going to actually have to be more. We're actually going to have a higher current flowing through R1. And now, if that's the case, how do we solve for with that equation? Now, with this equation, defining V1, no, I1, I2, IC, I2, that's R2. We have a value for R2. What else do I need to know? V4. V4 is a part of this equation. Now I know V5. Okay, so V4 equals 3.3, right? V5 plus 0.2 minus 0.5, 3. So, okay, let's assume V4 equals 3 volts. Okay, V4 equals 3 volts. 3 volts, right? And then now we have that V4, I2 equals 1 milliamp minus, or no, plus 1 milliamp plus I4, which I4 3 volts. We don't have a value. I'm just trying to think now. What do we want? So I2 equals this. What else did I have that described elsewhere? Well, I2 equals this. I1, I thought I put it somewhere. I didn't put that down anywhere. I1 equals I2 plus IC. Therefore, we know IC is 10, so 11 milliamps, right? IC equals 10, 1 milliamp, 11 milliamps plus I4. Wait, I2. Yeah, because that's I2 equals I1. 11 milliamps plus I4 equals I1. Okay, what do I want I4 to be? What, just 5 milliamps? Okay, let's assume a value of I4 equals 5 milliamps. Okay, then I1 equals 15 milliamps. And now R3, R5, I can solve for R2. I can solve for R2. I can solve for R1 equals. Let's see how that pans out. 4.5 divided by 15 e to the negative 3, 300 ohms. So that'll work. 300 ohms. Okay. I'll put some units. Ohms. R2 would be R2 would be 1 plus I4, which is 5. So 6 milliamps and a value of 0.5 volts, right? 0.5 divided by 6 milliamps. 6 e to the negative 3. 83 ohms. Okay, let me make sure of something first. Now, our power is, power for, I just really want to check this one too. Wait, right? Well, I guess, no, not necessarily. What's 15? That's probably our height. That's probably going to be our hottest one. So so our power going across resistor 1, P1, we'll call it 15 milliamps squared, 15 e to the negative 3 squared times our resistance value. Or rather, we know the voltage is 4.5, right? Okay, never mind. We can just do 15 e to the negative 3 times 4.5. Okay, no. We're way below our maximum power ratings, so that's fine. Okay, that's good. Okay, so now based off of our assumption, we've concluded with these values. Is that everything? V4? Yeah. Wait, I don't have a value for R4 though. R4 equals, let's see, V4 3 volts and what is it? 5 milliamps. So 3 divided by 5 e negative 3, 600. R4 equals 600 ohms. Okay, so now based off our assumption, we concluded, through reasoning, through logical reasoning, and through our KVL and KCL, we concluded on these values for our resistors. We're going to go ahead and build this in a simulator and see what the results are. So let's go ahead and do that. Okay. So like this, we're gonna have a guy like this. We're gonna have this guy up here like this. We're gonna have one going to ground. Bang. We're gonna have this guy over here. Bang. I want to move him over a little bit. Get him in line. Right there. Let's see this. I want everything in line. I want it to be perfect. Just like that. That looks good. And, wait. Oh, yeah. We need this guy, too. Oh, I guess I gotta still solve for... Yeah, I should, let's include him. I gotta solve for this, too, still, real quick. So let's do that. Okay. And then now I gotta solve for this guy. We'll call him R, lim. R lim. For our limiting current resistor. Current limiting resistor. So that'll be as simple as 4 minus, we'll just call it V lim for now, minus, which is going to be 1 milliamp. Okay, no. So 1 milliamp times R lim minus 0.7 minus, what's across I5? Or what's V5? V5, 3.3. 3.3. Okay, well. That doesn't fucking work. Shit, how did that happen? Ugh, what? How does that happen? It doesn't work. Oh, let's build this circuit real quick. We'll skip that. Let's see how this goes. Let's see how this goes. Okay, we're gonna need transistors. We got this good library right here, 2N3904. This is exactly what we're using in real life. Where's he? He's right there, right? Yeah, that's where he connects, and he connects to the base like that. That looks good. Okay, let's see how this goes. And if we need to, we can redo our theory. One megahertz is what we'll do. I have a little less, like 920 kilohertz, but we'll just do this for now. Yeah, also, I need one more thing here. Capacitor, coupling capacitor. Yep. That looks good. Let's add our values in. So this is R1, our value for R1 is 300. R2, 83. R4, 600. R3, 550. And I hate when it fucking does that. Okay, and R5, 150. 150. Apply. Okay. We're going to, this is our output here. Okay. We're gonna put a probe, voltage probe. There we go. Gotta ground it. Yeah. Oh yeah. Current probe. Meh. I think it just gives us our current anyways. Let's see. Simulation. We want a DC simulator to check the operating point, and then we have not an AC transient analysis. And we want to go to like stop at 1. Now we'll do 10 microseconds. Apply. Okay. All right, I like it. Simulation. Calculate DC bias. Schmidt trigger. Bang! Come on. About to drop a point. What the fuck? 0.0? Why is that so small? That's not good. That's not right. That's not right at all. Let's do it again. Calculate DC bias. That's like a 4.7, 9, 2.8. Shit, I don't know what the name of my PR1. That's what it is. PR1. Do I need to see more, or just maybe it's just not working? It's just not working. Okay, apparently that's not good. Let's let me add a. I also want to see this. What am I looking for? Probes. Nah, something's not right. 1 megahertz. What? PR2. What the what? Definitely not that. I don't know, that wouldn't have an effect on this, but like, nah, what the fuck is going on right now? Am I missing something? What's going on right now? There. Okay, there's my sine wave. Okay. Holy shit. It was really difficult. Alright. There. That's what I wanted to see. Okay. Alright. It's a little better. Give me 4 microseconds. Essentially 4 cycles. Why is the star looking like that? Is it the number of steps? Step 400. What's number 11? I don't know. 20. Like, why does it look so shit? Okay, that's better. Let's increase our steps more. Looking like real dog shit. 20, 50. How high can we go? Give me more steps. I want to see it. $9 volts though? Why? Really? Nah, really? I'm getting 9 volts? Because it's superimposed on 3? Wait, no. Because, yeah, because I got 4 volts peak to peak. We're at 3. That's like, why is it 9 volts? I don't want that. I don't want a 9 volt output. That's way too much. That doesn't even make sense. That doesn't make sense. Why would my output be 9 volts? Huh. What else was I gonna do? I guess decrease this. Let's go 3 volts. $3 volts. That doesn't even matter. That's looking good. I got, I'm looking at some square waves right here. So that's exactly what I intended. Let's do some more steps. Let's get a little more accurate. 50. Let's go. Let's go 100. Let's see what happens. Do it. Yeah, hell yeah. What? It's incapable of doing that? Okay. Alright, sure, whatever the fuck that means. What, can I go 55? Bro. Jacobian singular at t equals 2.5. Can I go 51? Bro, I'm literally at 50, huh? That's fucking incredible. That's incredible. Okay, sure. Why is my output 9 volts though? But I mean, it's saying it's working, so it's saying it's working. Now what if I put a resistor here? And we'd have to decrease this value a little bit. So imagine I have, let me think. imagine I have, what was it? What was my V5? 3.3 volts and zero point 0.7. Okay, so 3.3, 0.7. What if I went 3.3? What if I went, okay, 2.5 plus 0.7, 3.2. Well, now I went down to 3. 4 minus 3.2. Wait, does that even... That doesn't even... Wait. Wait, what role does that play? No. It's more like a large signal analysis. Oh shit, I'm not really sure how that works. I just need to monitor my current here, but I'm not gonna get anything through. So PR3, we can add that 50. Let's just make it 50. Let's just do a rough calculation. What I want. So if we have a 3, let's go back to a 4-volt input because that didn't change our output. 4 divided by, I want 1 milliamp, right? So 1 e to the negative 3, 4,000. Right, 4,000. Let's see what happens. Okay. Let's see what happens. And now to this, we want to add a PR. Is that it? Apply. Okay. Wait, that's what it was, right? PR3. Yeah. Hey, what's up, brother? Oh, great comment, great comment. Yeah, it absolutely is. Well, you know, we built an oscillator, right? Right here, we built this oscillator, which outputs a sine wave, and then now I'm building, and I put it through a buffer stage, which is the purpose of this transistor here. I don't got much lighting, do I? There you go. There. Okay, we put it through a buffer stage, right, so that we kind of like decouple it from any external load. And then now we're building a Schmidt trigger. Rather, I'm theorizing as of right now, and then we will build it. But I first did the theory, as you can see here on paper, right? Did the theory to kind of get an estimate for what my resistor value should be to bias the transistors to operate in saturation region. And then we went ahead and modeled it in the simulator. And then now, yeah, we're comparing the output so that we can know whether it's been good or not, whether it's been a good theory or not. And yeah, that's essentially what we're going for. We're trying to convert our sine wave into a square wave so we can have a clock oscillator. So we're on the right path, but like, I don't know why I'm not getting a current measurement. Like, why is my time dependent current 0 right now? I don't really understand that. Yeah. So, I mean, that's a little confusing, but I suppose, you know, we got the voltage output that we desired, right? We converted the sine wave into square waves. And, yeah, So I guess we could go ahead and build it. Honestly, we could build it. And then I'm going to solder it all on this PCB. I've yet to transfer the buffer stage to the PCB, but I wanted to build the Schmidt trigger first before I did that. But, you know, our output seems to have done the correct thing, right? This is our input sine wave, and this is our output square wave. So maybe I can mess with the parameters a little bit and see if we can decrease the output, because I don't want an output of 9 volts. That's for sure. I'm not really even sure how the fuck that's possible to get an output. Well, not that it's outputting 9 volts, but it's 6 volts, 6 volt output, right? But superimposed on a 3 volt, right? Like, what's, I don't know, it's really weird. Taking my reference from here, that's my output. Let's see what happens if I change some parameters. So, I don't know, let's increase the value of this, 550 to 1000. Just to see what happens. Okay, I don't like that. Nope. We'll go back, that didn't do anything, 550. Okay, just messing around a bit to see how these values alter the output. Pretty much the exact same. 83, we'll go back. Okay, not really doing anything for me right here, right here. Let's change this. Let's go a little higher, 1000. We'll see how that looks. Oh, Dino. Oh. Why do you do that? I thought that was like a real person. I forgot it was you. Why'd you do that? Totally forgot it was you. God. Thought somebody was actually fucking watching. Nobody tunes in, man. Nobody tunes in. Like, how in this entire time, I don't know that I've had one random person join. Like, what's yeah. Which doesn't even make any sense to me because, yeah, lovely to have you here. Thank you for being here. Just, yeah, I don't know. Not really sure why nobody else is joining. Like, it says current stream 5 views, so perhaps there's been people in and out, but like, I don't know, I guess just uninteresting. I just don't got it, or what? I don't know, but yeah, we're gonna continue to do what I do, so whatever. But yeah, it seems that yeah, our model is working. I just changed that parameter, which is like, what did that just do? It looked like it changed my frequency. To be real with you, it looked like it changed my frequency. That's weird. So what if I did a lower value here? What was I at before? 600. Let's go to 20 as a nominal value. Right, it's changing our frequency. That's really odd. What? So I can vary... Wait, so I can vary the duty cycle? Wait a second. Wait, that's PR2, right? We got P3 on here still. Get rid of that because I don't know. I don't even understand that, but whatever. Yeah, so I'll add about a 4,000 is what I have. I guess so. Let me change this back to 4 volts. Lovely to have you here, my sweet love, my sweet dino. Okay. Maybe my current, that's probably why. My current value is so small that I can't see it in comparison to these. So let's get rid of those now. Now I should have it. Let's see, PR3. Yeah, that's what it is. And what are we getting? We're getting 8.8 milliamps, 0.8. I mean, that's not enough. Let's 0.8 milliamps. Let's decrease this to, what is a value that I have? What actual value do I have around this? Let's siphon through our resistor values over here. My sweet dino. My sweet dino. Oh, I got a 4.7. That's too much. $1.5K. I could get 3K with two 1.5s in series. That's a possibility. I got a 2K. Let's see where 2K puts me, because that's far too little. 2,000. Apply. I don't know why that happens either. Like, what? What changed? So I can do 4,000, but I can't do fucking 2,000. I don't know. I guess I'm just missing the point here. And so now I can't do a simulation. Yeah, that's closer to where I want it. I'm not really sure what's going on with the rest of it. So, what if I did 3? That's exactly where I want it. Okay, so I don't know. We'll roll with that. I can do two 1.5s to get that. Let's see if this causes issues now to go increase the step size. Nope, good. Okay, that's exactly what I want. Looks good. I like it. I like it a lot. All right, let's change this now. Let's go back and see our voltage output. PRV2, I think that's it. Apply. Nope, that was our input. Let's see our output, which is 1. Apply. Okay, and we got a, that's a really nice looking square wave. So just the 9 volts output is crazy. The only thing I could do is put that through a voltage divider, I guess. So let's do that. Let's put it through a voltage divider, because I don't want that output. Bruh. Just go away for now. Get out of here. Oh. Yeah, rookie of the year, ladies and gentlemen. Rookie of the year. Absolute rookie of the year. Okay, let's just add a voltage divider. Let's see, lumped components, resistor, bang, bang. Well, then now this is going to change other things too. So, I don't know, maybe I have to put it through another buffer stage. This is going to change, like, everything. Unless I were to keep these values, delete, unless these values were to be much larger than any of the other, so like, I don't know, let's do, what do I want, 5,000, apply, and let's do like 10,000, and then we should have an output of about 4.5, or yeah, 4.5 volts, let's see, and then we're going to take the output from right here. Probes. Can you see that? Yeah. Voltage probe. Yeah, 4.5, right? No. No, that would be if they were both the same value. I'm at more. No, let's make it 4.5. So let's do 10,000 and see if this changes anything. Yep, approximately 4.5 volts out. Yeah, that's like exactly what we want. I guess let's build it and see what happens. Sure, that's the best part, right? Let's build it and see what happens. Whoops. Whoops. Okay. Alright. Oh yeah, but that's not okay. Actually, let's not quite build it yet. What do I have to do? Okay, let's convert these to actual values of, oh wait, this. I wanna take this back to around 600 because that was my theorized value. And now I got that fucking problem. Okay. That's so silly. So silly. I don't like it. I don't like it at all. I don't like it at all. Let's go 330. Maybe we'll do 220. If I have to, I will. That looks nice. It's a lot cleaner, right? These are kind of looking, I don't know, it's not looking super consistent. Not looking super consistent. What now if I decrease this more? 220. And what, it starts to look better? It really does start to look much better. So if I go even lower as far 150, and now we come into this problem. I should really look up what that means because it's starting to piss me off. 150. What other values do I have? I have a 47, 150, 47, 197. Let's see where that puts us. That's looking really clean. Yeah. All right, let's do that. That looks really clean. Okay, very well. Let's see what our DC values are. Simulation, calculate DC bias. Okay, 1 volt DC, right? Right, and that's why we start. You can see the square wave starts at 1 volt, right? It's the signal is superimposed on a 1 volt DC signal, and so I guess that's setting our 0 point. How interesting. That's why I should probably also add, I guess I could, whoops. Now we can get rid of that by adding a capacitor here. Whoops, lump components, capacitor, let me see. Oh, fucking rookie of the year, guys. Let me just keep doing that, so yeah, okay, I don't know, I'm gonna lose it. Alright, yeah, so adding a capacitor here. Cool, I just did a bunch of stuff without showing it. Now we're going to start at 0. That's probably what we should do. There we go. 197. Let's go back to 220. 220 and see how that looks. That looks really nice. Okay, that's a really good looking square wave. I like it. I like it a lot. And we're starting at 0 now that we've added the capacitor. It's a value of 1 picofarad. Let's see what happens if we do 10 nanofarads. This also might increase our, oh wait, did it decrease it or increase it? Our rise and fall time. Regardless, it looks good. It looks good, so let's go ahead and do it. It looks really consistent. Although it's beginning to lag behind our sine wave, which is not good. Why though? Perhaps if we did decrease this, let's do 1 nanofarad and see if it keeps up with our sine wave better. 4 microseconds. Let's go up to 7 so I can see some more. Excuse me. Okay, I want to add excuse me. I want to probe for the current that's flowing through here. Let's do this. I want to know what's going on over here. Whoops, not that. Schmidt trigger. Let's do a DC bias. Yeah, that's what I figured. That's what I figured. It's super low. 0.2. That doesn't make any sense either. But it seems to be operating. Shit. I mean, it's such a small current that, you know, it's like, what do we even do with that? What would that do? That would change everything. I mean, this is a really bad design to just have this voltage divider here. Like, that's not gonna do much for me. I guess that's why we would have another buffer stage, right? Another buffer stage after this. That would make everything much better. So, voltage divider though, would I still want that? I guess I'm still capable of doing that. Still doing a voltage divider. Well, would we need an amplifier at that point? No, because the current gain is what would be there. Yeah. You know, because if we used... Yeah. Because then what would happen? So imagine, you know, following this voltage divider, we had a buffer stage and the load, the impedance of the buffer stage, though. How would that go? I mean, we could probably make it around that value. I think that would be fine. Yeah. Right, 112 microamps. Right, with like a typical buffer stage with a DC current gain of 100, we could achieve 11.2 milliamps, right, for our supply. So that's a possibility, right? So we just follow with another buffer stage, essentially. Because that current is way too low to do anything important, you know, imagine we were directly supplying a load, like what would happen then? Imagine this. It's going to change everything, so... and then what? Could I go ahead and measure the current? Surely I could. So, you know, like what would we even be supplying though is the question. I'm not really certain of this. You know what? Let's go ahead and build this and we'll see how things go. 83. What actual values do I have? 83. You know, 22. If we had a 42 47s, that would put me at 94. That's a possibility. 94. Okay, so 47 ohms. Okay, let's say that then. We'll do 94. We'll see where that puts us. Let's see what else. We have 300. Can I achieve that with two 150s? I can, which I do have available. Two 150s. That's another 150 there. Right, let's change this value to 94. And let's see how this alters the circuit. Or alters the output at 94. We can achieve that value. 550. Holy shit. What was my original? For R3? Oh, it was 550. Okay, that was my original 550. Let's see. How could we achieve that? Well, we have 470. 470. No. I should have a 330. Holy shit, we could achieve that. I think I have a 330. A 330 plus a 220, that'd be it. And I should have this. I'm pretty sure that's them. Let's compare with our resistor code. All right, looking at this here. Oh, you can't see it. Hold on. Looking at this here. We have orange. We have 3, 3, and then a brown multiplier, which is a 10x. So 33, 330. Yep. So 330 and a 220. We're gonna need the 150, 330, and our 220s. Wait, do I need the 470 for anything? No. Okay, and then we have, two 1500s. Because I don't want to burn the base and our 220. 220. And then what? That's our 10K for our voltage divider. And where are my 220s? I got them. Where are they? Where are they? Where are my 220s? Oh no. Oh no. 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 Oh. Oh. Surely I have some miscellaneous ones. All right, let's look in here. What is the 220 code going to look like? It's going to be 2 reds and an orange or brown multiplier. Yeah, 2 reds and a brown. Right here. Here's 1, 2. But they're here. How many licks does it take to get the center of a Tootsie Pop? That's a 4. That's probably enough. You know, we could also make a Schmidt trigger with an op amp, operational amplifier. But let's keep using the transistors to get real familiar with their operation before we move on to the op amp. Bang! Let's go. All right, cool. So let's look at the simulation one more time. We are capable of achieving all of these values. Oh yeah, I did change this 94. So let's see how that turns out now. Oh, that's not what I wanted. Check error no action defined, nothing to do. You piece of shit. I don't know what the heck is going on. No way. Wait, invalid? Oh, I don't have it hooked up anymore. Let's pull out the handy dandy voltage probe. And let's just give her a try one more time. PR6 this time. Let's round it up. Let's get rid of the PR4 because it no longer exists. Do the time dependent. Oh yeah, I'd say that's a pretty nice square wave. With like a 3.3 or 3.2 output, that's... There it is. There it is. There it is. Absolutely. All right, the conversion of a sine wave into a square wave. So let's go ahead and build this circuit. All right. After I take a quick piss. But before I do that, I'm going to put on one of my old YouTube videos, or rather one of my earlier streams, so that you don't get bored. So let's hop on over here. And I really got to take a piss. Next step to technology domination, fixing my huge mistake, soldering my homemade oscillator. That's that's a highly viewed video. Actually, you know what? Rather than put on one of my streams, let's just put on one of my videos, my actual videos that I took time to make. Impulse response, op amp 2. See, there's the operational amplifier. I guess it's pretty applicable, right? We're just talking about it, right? I could also make videos on like biasing the transistor to operate mother trucker. Shut your ass up. I could also make a video about biasing the transistor in the for the saturation region and for the active region. I feel like that'd be a well thought out video. Let's see. Yeah, I don't want that. I want to keep that up. Let's full screen it. And I don't know, we'll just start it from the beginning. Alright, I'll be right back. I'm going to take a short break. Welcome to the stream, nerds. We're going to continue our frequency response. Kind of a continuation from the last stream. We're going to be working with the same circuit parameters, such as like the resistance values and the capacitance values, and I'm gonna draw it out for you, and then we're gonna do the analysis together. So we're gonna have a capacitor here in series with this resistor, be in series with this parallel circuit here. Okay, and we're taking the output, bada bing, that's the positive of the output. This here is connected to the inverting input of our operational amplifier. That's just another component. It's an integrated circuit, operational amplifier. Yeah, to describe it as an integrated circuit is like a very general description. Specifically, it is an operational amplifier. And then even then, there are many different kinds of operational amplifier. Positive, negative, V, and okay, and now we have a complex input, we have a complex output to do a frequency response. It's like a typical circuit, right? This is what the actual components look like in a schematic or in a circuit diagram. But, I guess we go about modeling it differently when we're doing impedance values and so I'll give you some insight into what this looks like. Alright, so it's really just like the very same thing, except we draw things as boxes. We describe them by their impedances. Capacitor with subscript 4. Instead of seeing C3 or C4, we're going to put it into its impedance form, which the impedance for a capacitor is this 1 over C3S. And where S equals, make sure you can see that, J omega. And so to convert frequency into angular frequency, this omega here, you just multiply the frequency by 2 pi. For 1 over C4 times S, where S equals this imaginary number J, which is J equals, so we'll just write all this out, equals the square root of -1. Right, that's your imaginary numbers. If you have J squared, then it itself is going to be -1. Right. This time, the frequency breakpoint specifications are the same, which was 10 hertz on the low end, 20 kilohertz on the high end. But we don't have enough degrees of freedom to independently specify the mid-band gain. Okay, so let's put down our knowns. I don't know exactly where it's applicable, but we have a 220 picofarad capacitor, resistors to pull from within a range of 100 to 100 kilo ohms. That's break free. Beautiful. You like that? Okay. So this is what we're working with right here. Okay, so we know that our break frequency is determined by this inverse of tau. This all makes sense, where tau itself equals, in this scenario where we have just capacitors and resistors, it's RC. Transient analysis, we're doing the frequency responses, right? So this doesn't have anything to do with time dependency. It's more like we consider it to be steady state. Okay, so it's honestly such a beautiful feeling when you've been struggling with something and then you persevere and you overcome the challenge. You know, it brings a sense of accomplishment, a sense of success. But this right here, this is what I want to know. Filters. With a parallel capacitor with the series resistor, we can achieve the desired voltage divider at high frequencies. Indeed. Alright, let's just jump into it. Let's just start. V negative minus VI. Okay, divided by the combination of 1 over C3S plus R3. There is a very minute amount of current that flows into the operational amplifier inputs, but it's so minute that it's negligible in reference or like in comparison to any other current flowing in the circuit. V positive itself is 0 right now, and in an ideal operational amplifier, the loop gain A, which is just one of the parameters of an operational amplifier, in an ideal op amp equals infinity, therefore making V positive approximately equal to V negative. This is what it's actually going to look like. It's going to be 1 over. Okay, so it's going to be R4 times C4S plus 1, and then R4 is going to go on top. So I'm going to go ahead and say that. So now we're actually going to have, and I'm going to put that on that side. All right, so we're going to make everything positive. VI C3S over 1 plus. Yeah, that's the thing though, that's not necessary. Imaginary or complex very forward. So we'll move everything over as we need to. VI R4 C3S divided by. Okay, now all this equals V out. I want to convert these complex variables right here and I'll turn it into the real. Okay, add it up here. So negative VI R4 C4 times omega. This right here, this one's gonna come down to this. Why is pizza always better the second day? Like, come over. Bro, the first day I had it, it just was not hitting at all. I was actually so disappointed. But like the second day come around, it's not bad. It's pretty fire, actually. I just don't understand though. I swear, it's always better the second day. Always. But here, we'll listen to this guy a little bit longer, and then I'll get back into the square wave. The real component of it. So now what I could do, we still have our break frequencies. Recalling from the last stream or the last problem that we worked on, it was 10, 6, 10, and it was 36171. Shit. 36171, that is right. Okay, 3617. So this is, you know, continuing from the last problem. These are our values of our resistors. And now this is R3. R3 equals, this equals R4. Okay, so that means C3 equals, here, I'm gonna get rid of this. That was not applicable. That was a dumb route. C3 equals 1.5 microfarads, and then C4 equals 220 picofarads. Okay, now what is the mid-band gain for this circuit? The mid-band gain. Okay, last time we want the mid-band, we wanted a gain of 2 at the mid-band frequency around 1000 hertz, 1 kilohertz. Again, to get our omega, hertz times 2 pi is going to give us our angular frequency, which is like 6,000 something, 1000 times 2 times pi. Okay, so you can see that, boom, 6283 be radians per second if we want to apply some units to our angular frequency. This is what we're going to plug in now for this omega here. We're going to see the outcome for some like arbitrary value of Vn, which means I'm going to pick it. I'm just going to pick a random value of Vn and see what V out is. So I'm just going to go with 5 volts. Okay. So this is what we're gonna do. Okay, we know what R4 is. We know all of our shit now. Okay, so 36,171. Whoops, 6283 times our -5. Whatever. We didn't need the negative really. Okay, we get a real small number. We're gonna do this. We're gonna go the square root of 1. R3 106. All right, let me run the calculation back just one more time. How about this? Yeah, let's do this a bit differently. 3R3 plus 1 times both of those, so I'm gonna do that. All right, ladies and gentlemen. Okay, 1 minus. So this is gonna change. Man, this changes quite a bit. Now, this is what we'll use, and we'll plug in 6283 again. Ah, man. Really? Alright. What is the mid-band gain? Let me explore another route. Right, because we got to this point. So, Arthur... Alrighty then. Alright, enough of that, idiot. Alright, let's get back into the regularly scheduled program. Back to the design board. Are we good? Yeah, we're good. There's 2 of you, yeah! There's 2, yeah! Right? Aren't we already sick of 1? Right? So let's not overdo it. Back into the building of our Schmidt trigger. Alright, we seem to have calculated everything correctly. We'll go back into our simulation. Here we go. All right, our simulation, right? We built our... Okay, so first we did the theory. Right, okay. First we did the theory. All right, we theorized it to get an estimate rather close to our desired, like... All right, so we theorized it in order to get close to our desired, voltages and frequencies. We theorized... Okay, wait. Let me do a succinct description of what's going on, and then you can like clip this. Okay, this would be the clip. So let me say it really well though. So Morty, all right, so first we fucking built the circuit in theory, right, so that we could get close to our resistor values, so that we can set the bias point for the transistor to operate in the saturation region, right, fully on, fully off. Once we found once we acquired an estimate, or rather, what's the word for it? It's not like our actual values, but it's like, just something to go off of, so that when we build it in the simulation, we have some sort of value that we can come close to, right? Like, I theorized a value for R1 of, okay, well, that one is exactly what it is. Shit! Fuck! All right, let me try this again. Okay. All right. Okay, first, I theorized it so that we could acquire some value for our resistors in order to theoretical values and experimental values. Are you fucking kidding me? With the theoretical experimental value shit. Are you kidding me? Nah, I mean, I guess you really did hit it on the target with that one. That was a bullseye. I ain't gonna lie. Okay. So first we found our theoretical values in order to, set the bias point for the transistors for them to operate in saturation region, right? Fully on, fully off, switch-like behavior. Then we went ahead and modeled that in our circuit simulator so that we could see what our experimental values might be, right? And so this is what we came close to. Now, I referenced the values that I have available in my, in my resistor cache, in my resistor, fuck out of here. God, I keep messing it up. I can't just stay focused on it, right? I can't stay focused on the goal. My vocabulary is limited and it's really showing right now. Okay? Okay, let me try again. Maybe one more time I'll have it this time. Okay. No, I'm not built for entertainment like this, okay? Okay. Alright, first we started with the theoretical values so that we could set the operating point for our transistors to operate in the saturation region. Alright, and then we went ahead and built it in a circuit simulator for the purpose of seeing how close to our experimental maybe we'll just stop it there. I don't think I should continue anymore with that. Maybe another time. Okay. Alright, I don't know what the emoji you put is. I can't really tell what that is. But let's just continue. Let's continue to do what we're doing. Alright, so now we're going to build the Schmidt trigger on the breadboard. I'm going to just keep all this connected right now. Okay, let's get our transistors out too. And I just spilled something with a lot of shit in it. So I'll have to clean that up later. But we got these nice power general purpose transistor assortment kit, right? Got this from Amazon. Helici, right? Beautiful. I wish we made them in America, but I guess we don't, okay? I enjoyed your, oh my god, I can't read it with that background. Wait, let me, that's better. I had some suggestions I want to share with you, but I don't want to spam your chat. Let's chat on Discord. Brother, I really don't use Discord. But if you're being serious, and I swear to God, if you're not being serious, and this is some sort of like fucking scam, or I don't even know, bro, but don't waste my time. Don't waste my time, brother. But I'll consider it. I will genuinely consider it. Okay? Thank you for commenting. Thank you for being here with me. I do love you for this. But let's get back into the regularly scheduled program, and I will consider your chat. Okay? Alright, so we got this nice assortment kit here, right? Looking real fucking sexy. Excuse my language. But right here, we're going to pull out the 2N3904. Okay, so let's get that. We're going to need two of them for this operation. And then perhaps we'll need a third one for the next buffer stage, but we'll get to that later. Okay, we got the 2N3904 right here, looking real nice. Oh my god, look at it. So good. Oh, it's so good. See that bit? Never get the focus to work. But it's looking good. Man, I think the Celsius is doing something to me. Got me hopped up now. I got feeling real energetic now. Alright, so like what I like to do now that I've been working with the transistors for a little bit is that I like to set the transistor and build around it, right? Because it's kind of like the central point. I wonder if I'm going to have enough room here. Also really need some new breadboards. Like, this is becoming very difficult. Wait, I do have another one. Oh! My camera's top heavy. Shit. Okay. I do have another one. But I don't have a bottom on it. Oh, well, I think it'll be okay. I think it'll be alright. Let's use this one, though. This one's a little crowded. So, let's go here. Yeah, I hope he's gonna work. Alright, I'm gonna do this. I want to bust him open a little bit. Pause. pause on that one. That was pretty, that needed a hard pause, okay? I just realized that needed a hard pause, but... Alright, I'm a little shaky. I think I got a little too much caffeine in me now. That's not good. I'm just trying to spread him a little bit. Pause. Alright, got it. It's looking good. Looking sexy. No pause, you know what I mean? Go on, though. I also want to jump that. Okay, and this is what I'm referring to, right? We got this build right here in the simulation, so we're referring back to this when we make these connections. Let's maintain that and let's not fuck anything up, okay? Like on my oscillator, when I forgot to put a ground there, I specifically forgot this ground right here, this yellow wire right here. And I was measuring it with my oscilloscope. I'm like, why don't I got any signal? Oh no, it's the end of the world. Why don't I got a signal? And then I come to figure out that I missed an entire ground. Like, brother, are you an electrical engineer or are you not? Okay? So let's not make these little mistakes again. But luckily it was a little mistake, okay? So there is room for mistakes, guys, you know. There is room for mistakes. Don't be too hard on yourself, even though I'm the hardest on myself, you know. Sometimes you just gotta relax, take it easy. Alright? Maintain the sanity, because if you lose it, you just might not come back. Alright? And I feel like I'm on the brink. I'm on the brink of not coming back, right? But we're chill, we're cool. Maintain that cortisol at a low level, right? No spikes. No cortisol spikes, okay? Alright, let's get some square waves from our sine wave, okay? We're going to do a little conversion here through the Schmidt trigger. So I got this circuit here. It's our Colpitts oscillator through a buffer stage. This is part of the power supply here, our voltage regulator and our two capacitors. This is part of, yeah, the cortisol spike. All right, chill. Don't remind me right now, okay? Got the buffer stage so that like we don't overload any of our oscillating circuit. We don't want to overload it and change any of the parameters. Otherwise, like it's not going to oscillate anymore, right? It's very sensitive. So we put it through the buffer stage, and now we're going to put this the output of the buffer stage into the input of our Schmidt trigger, which is going to convert our sine wave into a square wave. Let me think. Yeah, that is, yeah, okay. That's succinct and that's well described. So let's continue moving forward. We got our 2N3904 transistors, right? 2N3904 is just the model number. It's an NPN BJT, right? You could essentially maybe swap it out for any other NPN BJT, which NPN is the description of like the polarity of a semiconductor, well, of a transistor, right? Because it's like more than just a single semiconductor. But anyways, NPN, and then BJT, which means bipolar junction transistor, BJT, okay? All right, so we're going to do that. Let's start making our connections, and we have a lot of resistors that we're going to have to connect in series in order to get the correct values, right? Series, we're going to add them. Thank you. All right, so starting with R1, we have a value of 300, and we're going to achieve this with two 150 ohm resistors in series. Oh, almost got the focus. Come on, baby. Almost got it. Almost got it. All right, that's enough. Okay, that's good. All right, so let's do that. Let's throw this R1 down first, right? You already... Let's do it. Okay, and that's into the collector of our first transistor. Okay, and remember these transistors here. So essentially, when we model it in the oh, come on, motherfucker. Oh. Anyways, you can see that we have three terminals, right? We have one on the left, one in the middle, and then one on the right. On the right is our collector, so it goes emitter, base, collector in that order. Emitter, base, collector, okay? But our emitter is ground, and so it's kind of like a little counterintuitive when if one were to look at the transistor, maybe you would assume otherwise, but it goes emitter, base, collector. Our emitter is what's going to be grounded through a resistor, but like, you know what I mean. Okay. So we got this value, and this is coming directly from our power supply. So can you see this? Yes. Okay, so let's try to keep this like really clean. So we're going to go bang like this. And now the shitty part with the breadboard is that the breadboard introduces a lot of parasitic capacitance. And so I hope everything works as we, theorized with the simulation and on paper, right? I hope this parasitic capacitance doesn't ruin it. If it does, I might crash out. So let's see what happens. Okay, so now that's going to be, excuse me, Morty. Okay, that's going to be connected to our power supply. Oh my gosh, bang. All right, that's 300 ohms. Man, I'm fucking, the Celsius got me going crazy here. But let's have some more. Okay. All right, what's next? Next. Okay, let's refer back to our simulation. Okay, yep. So you see this? This is what we're doing. We just did this, this resistor right here. Oh, come on. There it is. Okay, let's do the 94 ohm resistor next, which is going to connect to from the collector of this transistor to the base of our second transistor. Okay, 94. And the way that we achieved this was 4794. Right? 2 47s in series. That's perfect. Yep. Thank you. All right. All right, we got these 247 ohm resistors in series. That's going to connect from the collector of one transistor to the base of the second. So this is kind of looking a little curved. And we need them straight. Yep. Okay, so we're going to go here, and then we got those bits in series. And we're going to connect him from the one resistor to the base of our second transistor. Yo, comment in the chat, like, I don't know, you guys fucking with this right now? You guys enjoy the electrical engineering? I mean, like, is the circuit building interesting and all of that sorts? You know, I'd love to do a lot of different projects, you know, get into a little mechanical engineering. I got to talk to, I got to talk to the missus. She has a lot that she has to explain to me, so she better start explaining, right? You know, we don't want to have to, I'm not even going to say it. You know, we're on YouTube, so I better be careful with what I say. Plus, like, you know, I got yet to build a community, right? And I don't know how much dark humor my community could handle. So I hope you guys are enjoying the stream. Please, like, follow me or subscribe, whatever you would consider it. And stick around because we have a lot more to come, right? We're just recently getting into the build of this oscillator. I've been working on the theory for a long time and trying to understand exactly how to do, like, small signal analysis. DC analysis is quite easy, right? That wasn't the difficulty, but the difficulty was in the small signal analysis, which comes from, like, you know, small signal AC. And so, yeah, here we are, though. Look at how far we've come to this point. Now we're building the Schmidt trigger to get a square wave output. This is like what is used in clock oscillators. This is what's used in computers, you know, stuff like this. Computers, all sorts of memory elements. We can also use it for pulse width modulation, etc., etc. That's pretty boring. Let's build it. Right? Who gives a shit, right? Okay. Okay, 220, just one 220 ohm to ground. Okay, we can do that easy. Oh yeah, I have these right here. Perfect, we got a 220. Super interesting. I love you, Dino. Thank you. I'm glad you think so. Fucking love you. God, so good. Okay, we're gonna go from him to ground. So I guess this is gonna be our ground right here. Right, we want to keep those close. Okay, got him in there. Is that a good connection? He looks dirty. Damn, he is dirty. Okay. Now I'm kind of curious. I wonder if I need to change any settings on my oscilloscope to read a square wave output. I don't think I do. I think it should just show up on the original settings, like for the oscilloscope. But we'll see. You know, we'll deal with that later when the time comes. Okay, I got my 220 ohm resistor to ground. So now we've covered these three resistors. 1, 2, 3. I just have this guy, and then these are values that I already have. Oh, I have him too. Bang, we're almost there. Almost there, and then we can get to the interesting part where we see what happens, you know. Might spark a little bit, might blow some shit up, who knows. Wait, not gonna blow up anything, at least not intentionally. Yeah, okay. All right, 220. We got a 150 from the emitter to ground of the first transistor. Actually, that's both transistors. So a 150, where are my 150s? Here they are. Bang, that's looking nice. Dino, it's a party. It's a party. Hell yeah. I like it. That's a nice little cat emoji. That's good. That's very good. That's very nice. Ladies and gentlemen. Bang! Let's do it. Okay. And now this is going to go from... Yeah, both emitters are going to connect to this, and this is going to go straight to ground. Let's see how we should do this. So I kind of want to split it. Let's go, because it's going to be here to ground and there. And then now I can connect both emitters to that point in the circuit with a jumper cable, a jumper wire. And let's do that. Where are my jumper wires? Woo! I found them. I need some more of these too. Alright, but it shouldn't take too much. I like this one. I like this one. Let's try to keep them the same length. Come here. Come here. So nice. Bang. Okay, and we got that. That's actually kind of like too long. Maybe not. Maybe I like this one more. Oh, wait, actually, for that one, it's not too long. For this one, it is. That'll work. So we're going to go here, here. That's a perfect length. That's a perfect length. Okay, and then we'll do him and him. Here, too, here. You know what? Actually, we could probably use another one of those. Let's see. Let's try it. Let's try to find it. Oh. Oh, there. Why is that so hard? There it is. There it is. All right, cool. Got it. Oh, got another one. All right. Oh, no. He's like barely not there. Wait, I can move. No, I don't want to do that. We'll get him to work. It'll work. It will work. All right. Now you guys got to stick around, right? We got to see whether this is going to output a square wave or not, or if I completely fuck the whole thing. So let's see. Stick around. Stick around to find out. Stick around to find out. Oh, I hope that's deep enough. Yeah, I think that should work. Okay, it's looking good. I like it. All right, now to the base of him. That's where our input's going to go. We're going to go through a 3,000 ohm resistor, which is going to be two 1.5K resistors in series. So we got these right here. Okay. Looking nice. Looking really nice. Hell yeah. Hell yeah. If you guys stick around long enough too, perhaps you will see me solder it. You know, if it works, I'm going to solder it. Yeah, I think so. If it works, if it's a really clean square wave, I'm going to solder it. And then the cool thing is my oscilloscope has two channels, so we can put one channel on the input and one channel on the output, and we can make a comparison between our sine wave and our square wave. Bang. Okay, we're like that, and we like this. Oh, wait. One more thing. Oh, that has to go through a capacitor. So, actually, it's going to go like this. We'll jump him from here to here. But I want to use that one for that. For the input. There. Yeah, here. Like that. Those are in series. And, jeez, I hope all of... Look at that. I put them right where there isn't a conductor. So let's pick a different spot. Okay, here. And wait, well, we could do that and then do that. Yeah, that'll work. Like that. Come on, bitch. There we go. Like that. Am I not? Okay, I'm not connected to anything else. Good. This is getting a little crazy. And that's going to be our input. Yep, our input there. Let's go ahead and do that right now. Like, let me just do that. Wait, and then that's that's this guy right here. So, jump over all of this. I guess so. That'll work. And that's our... Well, no, that's our input. Yeah, to him. Yeah, right there. That's what it'll be. Just like that. Oh, man. Man. I could have done this better, but whatever. That's fine. That's fine. Okay. All right, just why does he keep turning like that? Okay, like that. Can you still see that? Let me move him a little bit. Okay, like that. And then what is the value of our... It's a 10 nanofarad. 10 nanofarad. So where are my capacitors? Capacitors. Where art thou, capacitors? They were hiding. Okay, we need a 10 nanofarad. Looking like this baby right here. Oh yeah. That's a 10 nanofarad ceramic capacitor, right? 10 nanofarad ceramic capacitor. And he's gonna go straight from our input to our base of our transistor. And the purpose for him, he's a coupling capacitor. This is going to attenuate. Is that the word I want to use? It's a good word, but like, is that really the right word? Essentially, attenuate any DC voltage, right? We don't want any DC voltage to get through to our AC supply, and rather, well, that's not really much of a problem because we have other capacitors. Wait a second, I don't need him though. Wait, I don't need, wait. Yeah, okay. Wait, so I'm going to remove this capacitor here. I forgot I already had a coupling capacitor here, but I want to remove him. Oh, how's that gonna... Ooh, this might greatly affect my buffer stage. Oh, shit. I didn't think about that. Oh, shit. Well, let's see what happens. Shit. I think it really will, though. Won't it? Maybe not. Maybe not. Oh, man. What if I had two capacitors? What's that gonna... That's not gonna... It's just gonna change the capacitance value. Okay. Yikes. Let's see what happens. Oops. Okay. Okay, that's into the base of our transistor, and then we have that emitter connected there. Both of those are connected to the same node, and that's connected through a 150 ohm resistor to ground, and that's our ground there. Let's connect these two grounds. That's for that. Ooh, what could I do there? I could move him forward. Okay, I can move him forward. And I also need a supply too. Okay, that would actually be best if I... No. Ooh, shit. I'm kind of running out of room. Oh, shit. I'm running out of room. What am I gonna do? Oh, I could just go from there to there. That'll work. Okay, that'll work. Same shit. Right? Yeah, same shit. Okay. And that's our supply. Let's get I need a little bit longer of a wire. Just a teensy weren't longer of a wire. I'm not... this one will do. That'll do. That'll do, donkey. That'll do. Ice cream truck is here. Ice cream truck is indeed here. What's up, everybody? Thank you for joining the stream. Okay. Alright, so that is also our 9-volt DC supply. So let's connect him into the supply of this, which is going to be where? Shit, I don't even know where we're at right now. That's going to be right through this network. Wait, right here. Right here. That's our 300 ohm. That's our 300 ohm right there. And also connected to our 550 ohm. So they're going to have to connect in the same place. I haven't done the 550 yet, though. Have I? No. It's right here. Okay, just like that. Okay. Okay, right there, 150, 150. That's our 300 ohm into the collector of the first transistor, and then we have to have our 550 into that. And then what's here? That's ground. Why is that connected there? Oh, because that's our supply. Wait, that's our ground? Why is that? No, that's our input. I need a ground connection. Okay, that's what I need. That's what I need. That's what I need. Shit, son. Okay. Okay. All right, let's do that first. 550. How was I going to achieve that? How was I going to achieve 550? Oh, a 330 and a 220. That's right. So I have a 220 here. We'll do him. And he's connected also to the same right there. So, which is, yeah, him, the white guy. Bang, bang. Oh, this is getting so messy. Ugh. Ugh. Oh, this is disgusting. There, okay, and then 330, which is this guy. Alright, cool. Absolutely beautimous. Right, absolutely beautimous. We are IQ maxing, ladies and gentlemen. IQ maxers. Okay. 220 ohm. Okay, we need him. Shit. Don't have any more 220s? I don't. I have to pull another one out. Which I spilled them all. I see one in front of me, though. Cool. That's a 220. That's a 220. From the base to ground. From the base to ground. Okay. Oh, did I already do him? Oh, I already did that. Okay. He's in there. Okay. So I think we got all of that. Let's connect our ground. I don't want to, yeah, I need to keep it as short as possible. Shit, I don't like this. I don't like how messy this is. And I don't like, I don't want a bunch of, I don't want real long connections, right? Because it's going to increase the impedance of the circuit, right? Granted, it's very small, but, still going to cause problems. Or potentially could cause problems. So, well, we could have him connect directly there. That's not going to work, though. I could just jump him. Yeah, that's what I'm going to have to do. Right? Isn't that going to work? That should work. Jump him. There's nothing else connected there. That should do it. I just don't want to, I don't want to do that, though. So let's do, oh, fuck. Like that. Like that. Yeah. I feel like that's the reason it sparked before, but let's see if it works this time. I can't have those guys touching. That's good. That looks good. I think that'll do. Okay, like that. Let's get these guys over here. Like this, and then now we can jump our ground. Yeah, go straight to the point of ground here, which is going to be like here. And where's our ground? Right here. There. Oh, shit. This is getting crazy. Okay. Alright, I really hope this works. Okay. Damn it. I don't like that. Get out of here. This wire's all up in my way. There. Something like that. There. There. Yes. Okay, that's better. That's better. Okay, you can still see that? Cool. Got a lot of connections going on. Why aren't you in there? Get in your home. Why won't you go in your home? Oh my gosh, these are looking real messy. Oh, fuck. Oh, no, okay. I need some space on this. Nah, it's looking all right. It's looking okay. All right, yeah, it's looking good. It's looking good. Okay, I'm really hoping that 3000K resistor doesn't mess everything up. I'm really hoping that it doesn't mess everything up. All right, so it's looking good. Got about, well, it's not looking good at all, but like, we got to do what we got to do. Everything as far as connections are looking good. That's where it should be. That's where it should be. That's where it should be. Yep. To the base, to the emitter, which are both connected to him, to ground. Got 220 to ground, connected to the base there. He's connected to the collector. That's our 330, 220 to supply. Okay, and that's our 550. Okay. All right, now we just did him. So I think we got all of this. We are grounded. Yep, we're grounded. Okay. Oh, shit, okay. Grounded. Now we just need these coming from the collector of our second transistor. That'll be easy to do. And then we just need these two 10K ohms in series. I think that's it too, yeah. Okay. I want to move him one forward like that. Bring these guys over here, and then we're going to take our measurement from right here. Yes. And then he goes straight to ground, which isn't really possible right now, right? Can we get it? Oh, we got it. Yep, just like that. Okay. All right. All right, let's connect our supply, which might kind of be a bitch, but let's give it our best shot. I need to remove this. Oh, we still need one more thing. That's okay, it'll be easy. One more thing though, we need a 1 nanofarad capacitor at the output. But that's not difficult to achieve. Can you still see that? Yeah, I'll bring him a little more this way. Just like that. We need him connected here. Oh, fuck you. Him connected here, him connected here. Oh, shit, come on. Yeah, like that. There. Okay. Oh, my gosh, okay. Alright, I really don't want to mess anything up. That's all connected. Okay. Ooh. Alright. It's looking good. You guys can see that. Okay, last thing. What is the last thing now? We got all those connected. That's connected. That should be good. Make sure none of, oh god, these are kind of like looking crazy. Oh fuck. I gotta fix that. Okay. That's okay. He's looking crazy. That's good. Okay, that's good. Yeah, okay. That's grounded. Oof, okay. Oh man, I don't know if we're gonna get an output on this, but let's just let's give it a shot. So from there, we need a 1 nanofarad capacitor. That's not looking good. I need a good connection here. That looks fine. Alright, yeah, that's good. Alright, none of these are touching. Okay. Yep, that's good. Okay. Whoo! All right. Okay, 1 nanofarad capacitor. Let's find that. We got him right here. All right, let's connect him. Just gonna go like this, and that's our output right there. So we can just grab a little wire like that. Shit, I also need a ground that's close. Yeah, that'll work. Like that. That should do it. Okay. Oh no. Moment of truth, ladies and gentlemen. Okay. Connect our oscilloscope. Oh my gosh, moment of truth. Okay. Okay. I think that's, let's get it off of there. Oh man, let's get it off of there. I think that's metal. I don't want, because that bottom of that is exposed. I don't want that. All right, connect him. Okay, numbers guy. Get away from him. Fucking so close. There. That is our ground. That's our ground. We got that. We got our supply into there. Going there. Connected through the capacitor to the base. Connected there. One thing. Okay. Safety first. Okay. Can you see that well? All right. All right, nothing. Okay. Oh shit. Okay. Okay. I don't know if I need to change the parameters on this. Oh no! Let me look something up real quick. FNRSI. Okay, let's just ask AI. FNRSI 2C53T 2C53T. Do I need to change oscilloscope settings to C square wave? For most standard square waves, you do not need to manually configure complicated settings on your. Simply press the auto button on the front panel. It will automatically adjust the voltage, scale, time, base, and trigger to display the signal. However, if you want to measure the square wave display clearly and accurately, you may need to. Ah, fuck. I mean, something's happening. How's it going? Not very well. Something's happening, but not the right thing. Let's see. What did I do with that? I put that shit away. Shit. Let's vary the voltage gain and see if this alters anything. I don't know. It's not definitely not giving me what I want. That's for sure. That's for sure. How long have I been streaming for? Damn, almost 3 hours. Not very good. You know, it might it might ruin my transistor, or at least one of them, but like, you know, I kind of want to just remove these resistors and hook up the what's the output of the buffer? Yeah, it's like kind of want to get rid of these. Let's see what happens in simulation real quick. Yeah, let's see. I just want to remove this resistor, to be honest with you. Shouldn't be, I don't know, shouldn't be a problem. Wait, that's not what I wanted. Come here, come back. What about, well, it's not going to give me anything. Wait, so PR3. Let's get rid of this, delete, PR3. PR3, right here. 0.035. I mean, that's okay, right? That should be fine. Let's remove them. Fuck it. Let's remove them and see what happens. Oh, you couldn't even see it? Fuck. Alright, well, I removed the resistors right here. Alright, that's our 3000 ohm resistor was right here. I removed it, and then this is the result. We got, that's 35 milliamps. No. Okay, what if I remove 1? So we only have 1.5. You can see that? Yeah. Come on. Bro, what's with this Jacobian singularity bullshit? Holy fuck. Oh my god. I'm gonna lose it. It's still happening? I'm just gonna remove it and see what happens. Like, fuck this simulation. It's on some bullshit. Fuck this simulation. Let me try it. You can't see this now. Hold on. I'll get you back over here. Man, I think this breadboard's also kind of fucked too. I probably shouldn't have used it. Oh man, I think it is so messed up. I don't know, let's give this a shot. No. Do an auto. Definitely not what we wanted, guys. Definitely not what we wanted. All right. I think perhaps I built it pretty shittily on the on here. So maybe I should I feel as though I should solder my buffer stage. Yeah. I feel as though I should solder my buffer stage so that we're not introducing any more parasitic capacitance, like at least not more than needed to be. So I'll solder the buffer stage onto the PCB, and then we'll go ahead and model the Schmidt trigger on the breadboard alone, because the breadboard is a little overwhelmed right now. It's kind of like ridiculous. So so yeah, I guess let's do that. I do want to take a little break. How many people do I got in here right now? I still got I still got 4 of you guys. I mean, it's like nothing, but like I'm super happy about it, right? I really appreciate you guys being here. Hell yeah, that makes me feel so good. So I guess let me just continue. Like, why? Let me not take a break then. So I'm gonna transfer these components here on the breadboard, right? I'm gonna transfer this stuff, or well, not this stuff, but this breadboard at least. This stuff right here. There's resistors in this transistor. That's my buffer. That's my buffer circuit, and we're gonna transfer that over to this side of the PCB. And we should leave some more room for the remainder of the Schmidt trigger, right? Because I want that all to be on one PCB. But we'll go ahead and transfer that, and then we'll model the Schmidt trigger on the breadboard and hope for the best, I guess. Alright, so we'll get rid of him for now. Alright, let's go ahead and transfer him. I want to think about how everything's going to lay out. Alright, that's into here. Okay. And that's there. Okay. I'm going to have to jump that. Right. Yeah, we don't want that. I could just, yeah, we could do it like that. Right, we could cut him, just go straight there. I think that's probably gonna be best. So let's go like this. What do I got? I don't know if I have enough for that. Let's get rid of that. Do some more, but geez, hopefully not too much. Okay, we jumped him to there. Then we're going to have, yeah, him, which is also connected to him, which that will work. Yeah, that's our output. That's our input at our base. Yeah. Okay. And then that's connected to there to ground. Okay. Shit. Where's let me get this. Wait, what? What the what? Wait, what did I just have? Yeah, that's the buff. Yeah, that's it. Okay. Hmm. I want to be as efficient as possible. And our left side, yeah, the left side's ground.
Nah, I don't like doing that. I ain't gonna do that. Actually, fudge, yeah, I will. I will do that. Okay, you fucking prick. Okay, and let me double check everything. So, through a coupling capacitor into our base, our emitter is connected through this series network right there to ground. At our base, we have this voltage divider. Yep, right there to ground. Yep, through him to ground, that's connected to the base. Yep. Okay, and then our emitter, or our collector, is connected directly to the voltage source. Yep. That's that. Okay. Put at the base. Yep. Okay. All right. Yeah, I guess let's move on over to the soldering station and get it done. Sure. I believe everything's right. To ground. Yep. Wait, what about... Wait, so that's connected to ground? Okay. See, I almost fucked up. I really almost fucked up. One of these at the base needs to be connected to the supply. That's the 7600, which is going to, well, that's the 10K. That's the, 470. So this circuit here. I have it grounded, but it needs to be connected to the supply, not ground. So let me fix that. Almost really fucked up. Okay, there. There you go, you little pussy. Little fucking pussy. Okay. Alright, my bad. I just wish he would cooperate. And that's going to be, that's a 5.6, and what's that, a 2K? Yeah. Yep, that's exactly what it is. Alright. Almost really messed up. Alright, bang! Alright, let's transition and solder this bit. Do I still? Nope, I don't. Okay, let me do something real quick. Okay. Okay, that should do it. Bang! Okay. That should definitely do it. I gotta hook up a bunch of shit. One moment. Oh yeah. Oh yeah. Oh yeah. Oh yeah. Oh yeah. Yep. Is that on? That's on. That's on. That's on. I gotta also, what else was I gonna do? Oh yeah, I gotta wet this rack. think I got too excited earlier. I kind of lost my voice. No. Okay. Alright, I like a value of 730. So let's do that. 730. Bang. Oh, shit. Alright, cool. Let's do some soldering. That's not enough. Come on, brother. There we go. Oh shit. Where's my PPE? Oh. Oh no, I lost my PPE. Oh well. Oh shit. Got me. It bit me. Alright, let me clean it up a little bit. I got too much wires going on here. So I'm gonna pull you back over here. Shit, what do I have to clean this up though? What did I use last time? What the heck? What did I use last time? I know I got a really nice, like wire cutter, but I haven't seen it for a while. But I must have had it last time. Ah, this one. That's right. That's right. Bang. I need to solder this guy. He's annoying the shit out of me. Okay. Oh my gosh, where's my PPE? Oh no. Shit keeps splitting. Found it. Oh, I'm gonna spill everything. Please don't. Okay. Back in business. Okay. What? No. Fuck no. Alright, let's do another clean. Fuck, dude. Yeah, fuck that, too. That's so annoying. I can't believe that came off. Yeah, kind of ran into a problem. I'm not sure how that's gonna work. I feel like I should just go ahead and clip that off. Get the fuck out of there. Shit, now I'm pissed. Alright. It's all good, though. It's all good. Oh, man. Pretty elaborate circuit. We'll deal with that in a second. Alright, let me just finish all the rest of this. come back over here. Okay. Okay, let's try this. There, okay, cool. That should be okay. Alright, nice. It's not enough. Shit. That's good. That's good. One more. Yeah, it's I'm just gonna leave it.
It's lead free, but still.
Oh, we got one more right here. What the? There.
Okay.
Alright, let's check this out. Damn, almost been going for 3.5 hours.
Hey.
Yeah, I think that's it. And then our output at the emitter. So let me just let's just solder a wire there. I think that'll be good. Yeah, I'm gonna need a pretty long one. Where's the one I cut earlier? This one? That'll be enough. Yeah. Shit.
There we go. I think I need oh no, I got that. Right. Yeah, that's way better. Okay. All right. Okay, so now we can just hook this up, right, and ensure that ensure that all our connections are right. That's what we'll do. I'm gonna put this back. Like that. Let me make sure these aren't twisted. Nope, that's right. Just like that. That's good. That's good. Okay. All right, let's get our oscilloscope hooked up and let's make sure that this buffer turned out correctly. Looks good. Grounded, connected. Looks good, man. Looks good. Let's try it. Yeah, okay. So our buffer is connected properly. Beautiful. Progress. Yeah, I didn't get a square wave. I don't know if you're here for that. I didn't get a square wave, so I think it might be due to because of like I don't know, my wiring the wiring on the breadboard was just absolute shit, right? So I here, let me zoom out a little bit. So I soldered the buffer stage to the PCB and that's down here now. Where's my hand? That's down here. But let me zoom out a little bit so we can see that better. Too close. Whoops. I don't know why I did that. But anyways, yeah, so I got the buffer stage right here. All of that, it's really hard to see right now. Whatever, but it's soldered to the board and we have the output that we desire, right? So we got that. It's looking good. I want to turn that down a little bit. Where, turn him off. Where is that at? Here it is. Yeah, I wanted to output 4 volts. It's looking really good right there. Yeah, okay. Yeah, so we got the buffer stage soldered, and it's good. So there's that. There is that. Okay. Bang! Okay. So, buffer stage was soldered successfully. I don't know, we can go ahead and try the Schmidt trigger again. I don't want to use that breadboard. I'm going to use this other breadboard. And, oh my god, too many resistors. But it is what it is. But good thing the buffer still works. Beautiful. And it's going to rise to an output of 4 volts, correct? Let's ensure it does that again. Yeah, good enough. It's getting up there. That's the only thing, right? You know, and I may have a problem that, like, right, so so if I have my oscilloscope in the 1x on the probe, right, there's a switch, I can go from 1x to 10x, which changes the capacitance perceived by the circuit, you know, the capacitance of the, the input capacitance of the oscilloscope itself, essentially. So if it's in the 1x region, it's like it's around, I think, 100 to 200, picofarads. I think that's correct. And then when it's in the 10x region, it's like within 1 to 2 picofarads, right? So we have like 100x difference. I think so. You know, maybe a 10x difference. Maybe it's like 10, 12, but I think it's 1, 2, maybe 10, 12. So maybe like a 10, right? Because it's 10x, right? Okay. Anyways, that's probably accurate. Anyways, we have this large difference here. When I measure the output of my oscilloscope in the 1x region, when it has a larger capacitance, we get a voltage output of, you know, we can change it within the 1.2 to 7 volts range, right? When I change the probe to 10x, which has a much lower input capacitance, we get a measurement of like 700 millivolts, like within that range. So I'm not really sure what my I don't know what to expect my Schmidt trigger to perceive. I don't know if it's perceiving this. So what would that depend on the capacitance of the Schmidt trigger? Perhaps. It's definitely not that small. It's larger, right? Just like the 1x. So perhaps it would be okay. It's not as small as 100. Wait, that would be, yeah, no, it's not as small as like 1 or 10 picofarads. It's not that small. It's much, you know, it's even larger than the 100 picofarads as the 1x would suggest. So, So I think actually we'll be okay. Considering this, that must be the logic behind it. I think it'll be all right. Shit, but yeah. Oh, all right. All right, let's do the Schmidt trigger. Let's rebuild it, and let's try this again. I'm not gonna give up yet. Well, I'm never gonna give up, but like for today, you know what I mean? You know what I mean? All right, here's this ugly mofo. I guess I'm gonna transfer everything over here. And that's how it was, right? Everything's hooked up, right? I guess we'll figure that out. Shit. Okay. Okay, so 300. We'll start with that. 150. Where's my 150s? Right here. That's probably it, right? That's my input, 150. And then what's this guy? What's my other input? 550, which is a 220 and a 330. Yes, okay, so. Yeah, that's my output from here to here. Do I have more room? I do. Yeah, I won't have those either. Yeah, let's not do that. Okay. Never give up. Exactly. That's the kind of mentality we need. Absolutely. I will never give up. So true. So true. Just so true. So true. So true. Oh, cheers to that one. All right. Let's transfer over here. Let's just transfer over here. Collector. That does go to the collector of our first transistor. That is right. That is right. Okay. Let's do that then. I mean, this should, wait, what is the range on this? Wait, let me see something real quick. Oh, I don't want to hurt my oscilloscope. Oh no. Shit. Bro, what? I just highlighted all of that for a reason. Yeah, it's not really changing anything, so we'll just stick with the 1 nanofarad. Sure. Okay. Yeah. Stick with the 1 nanofarad. Okay. I don't really see any purpose as to moving to a new, yeah. But the one thing that I do want to do, no, let's just put all this back. I guess. I don't know. I don't really see any purpose doing that. That's going to be way harder. And that's our input, which is going to go from here. Oh, that's going to go there. Oh, shit. No, I still don't like it at all. And I do want two 1.5Ks. Which was this one? Yeah, 115. Okay. Okay, and I do want that. I am gonna kind of redo this because
I don't like it at all.
I reckon. I reckon. Oh, fuck. Okay. Very tedious. Very tedious. I mean, for real? Give me something like half the size of this. Holy shit. I mean, and that's too small? Or will that work? That will work. Maybe if it decides to go in. kind of want to just solder a wire for the ground because I don't want it to be too long. That could cause issues, but I also don't want to disconnect anything right now, so I'm not going to. Let's hope that this will cut it. That probably will cause issues, but let's see. Okay. I mean, everything's looking good so far. It's looking, yeah, it's a lot better this time. Fucker. Okay. And that's our output connected to the collector. And that's input right there. That's our 9 volts right there. That's that. All right. I think everything's connected. Let's give it a try. Is that gonna stay on there? And he's connected well? No, he's not staying on there. Just turned it off. I didn't mean to do that. All right, let me solder a ground wire so that we can have a much shorter connection, and
because I don't like this long ground wire. The positive isn't much of a concern, but I feel like we're kind of close, right? Like this is beginning to resemble a square wave, maybe. Although it's very low, or very, yeah, like it's such a small voltage. I don't know. You know, this might be a problem. I might not be having enough at my output. Might be the problem. I might have to put it through an amplifier stage. This, yeah, it might be the issue. Let's try a shorter ground, and then we'll see. So I can leave all of that connected. I just need to disconnect this guy. And then, yeah, pretty short one. This yellow guy should work, right? Maybe a little bit longer. Oh, shit. Oh. I just want to see that square wave. I mean, I still don't need it to be that long. It's kind of too long still. Shorten it a bit. we ain't getting shit. Let's let's try a 10 nanofarad capacitor. Not it, guys. Not it. Our Schmidt trigger is not working. What else could I do? I just don't. Like, imagine we built the whole thing. What, I have the buffer too. Let me see if I still have everything saved. Fudge. Oh man, guys, not happening.
Our oscillator and buffer's working perfectly. Just, shit, we're just not getting it, man. Our Schmidt trigger is not working as intended. Let's try something, though. Let me try something. So, can I control copy this? Okay. Let's save. Did I save it? I think so. Let's open recent. Let's go to common emitter. I think this is exactly what I have, other than this is 10 nanofarads. So we'll change that. How do I zoom out here? Yes, well, whatever. Okay, there. Okay. Okay, there's our Schmidt trigger. Let's file save as square wave. Let's go open our buffer. We'll change the values. It's not even at all what my values are. Wait a second. Really? Is that really my latest buffer? Schmidt trigger. Emitter follower. That's it. That's it. Come on. Okay, control copy. Let's go back to square wave. Bang. Okay. Whatever, that's fine. Okay. Fucking, okay. I hit escape I don't know how many times and it stayed on the zoom thing, so I don't know. And why isn't that working? Okay. Okay. Not very happy that this didn't work. Alright, zoom in again for me. Holy smokes. Okay. This gone. Delete. Delete. 10. Mother trucker. I'm good. 10 nanofarads. Is this my output? This is my output. No, it's not. Is it? No, it's not. This is my output. Yeah. That's my output. Why the fuck do they look like that? Because that's 11, that's why. What? Am I missing something here? Is this not right? 1 nanofarad, 4.7, 33. I'm pretty sure that's all correct. To the... that's not correct. What the shit? Is that 10? That's also 10, right? Oh, I don't need him. You fucking... Bro, what the fuck? Get the fuck out of here. Get out of here, you fucking idiot. Get out of here. Get the fuck out of here. Whatever, that's fine. Oh, what the fuck? That's literally time dependent, right? Oh, what? Okay. Wait a second. So, wait. That's the ground. 150. Right. Actually, that's not necessarily true. What is this? What is this potentiometer? 102. So what does his value vary by? Oh, where are my potentiometers? Is that accurate? That's from the emitter to ground. From the emitter. Oh, those are 220 to there. That is 220. Hold on.
I don't know. Shit's not really adding up.
What the fuck? Why does it look like that? Four microseconds. 50? I'm so confused right now. Why does it look like this? Nanofarad 4.7. I'm pretty sure that's correct. Well, that's not correct. None of those are even micro. That's correct. Oh. And then yeah, it's gonna begin oscillating. So let's start at 10 microseconds and go to 15. Jacobian singular, Fuck, I hated Jacobian singular. Fucking idiot. Just do your job. Alright. Still fucking... Okay, you know what? Let's do this. So let's start at 1 second. Way past the startup time. Holy shit. And go to 1.12345. 1, 2, 3, 4, 5, 6. Oh my gosh. Okay, I guess that's really difficult. I guess that's too hard for my computer to do. Okay. We don't need to start that late. So we'll go let's just go 100 microseconds and do 105 microseconds. I guess 1 second was a little crazy. Super unnecessary. Let's see how difficult this is. Let's see the difficulty of this. Come on, baby. Give me something. Give me something. Man, I need to go. Okay, there. All right, cool. Fantastic. All right. Let's connect this and let's measure PR9. All of these values are correct to what I actually have on my circuit. So let's do this and take a gander here. I'll come over soon. Sorry. All right. Let's take a look at this. Let's add our PR9. And we got the same thing pretty much. Okay, that's exactly what I want to see. Our buffer stage is working. What's our output? Yeah, it's around that. Okay. Buffer stage is working. Let's go into here. Okay, through a, right now I have a 1 nanofarad capacitor, so let's do that. 1 nanofarad. See what that does for me. I'll keep that. Okay. And let's, oh no, wait, actually that is a, wait a second, 1 nanofarad, no, wait a second. That is a 10. And then I can get rid of this guy. Wait, that actually might be desirable. Anyways, let's see. And we want to measure PR6. Let's see. Okay, I changed a little bit. Okay, that's fine. PR6. Bro. Bro, what's the problem then? Maybe it's just the breadboard? Maybe the breadboard, but like I can't transfer it to the PCB unless the breadboard works. Like I'm just not gonna do that. But look at that, it works. Why is that? Wait a second though. No, that's right. I mean, that's literally the circuit I built, so I don't understand. I don't get it. Colpitts oscillator, buffer, Schmidt trigger. And that's the circuit I built. That's what I have here in front of us. That's literally what I have here in front of us, down to the exact parameters, the exact values that I've put into the simulation. We're getting a square wave in the simulation, but we're not getting a square wave on my oscilloscope. Could it really be the breadboard? Let's go ask AI. Let's go ask AI, I guess. See what he has to say about the matter. Shit, man. Can't believe it's not working. So I modeled a Colpitts oscillator to a buffer to a Schmidt trigger, all using transistors, no op amps. I'm not even gonna say op amp, transistors, and ran the simulation, with the exact parameters I have, with the exact parameters used in my physical build. So I modeled a Colpitts oscillator to a buffer to a Schmidt trigger, all using transistors, and ran the simulation with the exact parameters I used in my physical build. The simulation returned the desired behavior, a conversion from sine wave to square wave My physical build measured with an oscilloscope did not. I have soldered the oscillator, the Colpitts oscillator and buffer stage, and have the Schmidt trigger connected, solder the Colpitts oscillator and buffer stage to a PCB, and have the Schmidt trigger connected on a breadboard. The physical build is not returning the same output as the simulation. Why do you think this is? Motherfucker's gonna tell me, oh, the parasitic capacitance in the breadboard. Gap between a perfect SPICE simulation and real-world breadboard circuit is a classic hurdle in analog design. When an oscillator buffer Schmidt trigger chain fails to switch clean in hardware, it's almost loading effect or noise that simulator did not account for. Here are the most likely causes for the physical circuits mismatch, ranked from most common to least common. Yep. Colpitts oscillator and buffer on a PCB, but your Schmidt trigger is on a breadboard is a major red flag. The issue: breadboards introduce roughly 2 to 5 picofarads of capacitance between adjacent rows and significant tray inductance in the jump wires. The result: the high-frequency sine wave from your buffer is likely leaking across rows or picking up ambient electromagnetic interference. This parasitic capacitance can filter out your signal or cause the Schmidt trigger to oscillate uncontrollably at the switching threshold instead of snapping cleanly. Impedance mismatch and buffer loading. Your buffer's job is to isolate the oscillator from the Schmidt trigger, but it might not have enough muscle in the real world. Issue: BJTs have an internal property called input capacitance. When the Schmidt trigger's first transistor attempt to switch, its input impedance drops sharply. If your buffer stage has a high output impedance, the Schmidt trigger will load down the buffer. This severely distorts or shrinks the amplitude of the sine wave arriving at the Schmidt trigger's base. If the voltage peak no longer crosses the upper trip point, the trigger will never flip. All right, ladies and gentlemen, thank you so much for joining me today. I got some diagnosis here, or diagnostics, right? So I'm going to put the circuit through this eventually. That'll be probably the next stream. Yeah, that's very disappointing that we didn't get a clean square wave. So it could be due to a couple of things. We could be overloading the buffer stage with the Schmidt trigger, which is pulling down the amplitude. And I feel like we did see indication of this, right? We barely got anything out. We got like we still got like some really noisy oscillations at the end of the Schmidt trigger, but it was all the way down to like 5 millivolts. So I feel like, we could be overloading it for one thing. Also, we have to consider the parasitic capacitance in the breadboard, and all of this, bull crap, right? So those are things to consider, and as AI suggested, it gave us a diagnostic that we could follow here, and this is what we're going to do in the next stream. Because I'm going to get those square waves, all right? We're going to get a square wave oscillator, and we're going to do it. We're going to do it for sure. So, to conclude here, we did get our buffer stage soldered onto the PCB, so it's a lot cleaner. And, we did get the, we measured the output of the, following the buffer stage, and it was good, right? So we have our Colpitts oscillator here that consists of a common emitter amplifier centered around this 2N3904 transistor, NPN BJT. And then we have a buffer stage here, also consisting of a 2N3904 NPN BJT, except this time we assume a voltage gain of 1, whereas the voltage gain at this oscillator is high, right? And it must meet the Barkhausen criterion. So, we got that done. We did a good solder. We have a well soldered job. Right here you can see all the nodes that I have filled, right? And then we have our disgusting Schmidt trigger that didn't quite give us what we wanted, what we desired. So that's okay though. We're gonna run a diagnostic next time, and we're gonna figure out what's wrong with it. But this is all a part of engineering, right? What truly makes a great engineer is one's capability to problem solve. So that's exactly what we'll do in the next stream. Thank you so much for joining me, you guys. I really appreciate and love you.